Welcome back. I wanted to flip around something I said in the last video where I kept mentioning that pointers are hard and we all struggle with pointers. That's certainly true, but let me turn that around and mention that, once you get a handle on working with pointers, and you will at the end of these programming practices, you're ready to go. And I want you to think of it from that perspective. Yes, there's a little bit of a hill to climb here. Once you have a reasonable handle on pointers, nothing's going to phase you in the rest of your at least academic programming career here. So keep that in mind. There's a journey here, but the destination is real preparation for the rest of your programming career, and we should embrace that challenge. And so let's work on a couple of reasonably challenging examples together. But before we dive into that, I want to make sure I cover this concept of dynamic memory allocation a little bit better. In the last video, we kind of just left off here, and I mentioned there's this function called malloc for dynamic memory allocation, and this was all correct. And so one takeaway is you want to allocate 15 integers. You use this function with this syntax. That is in fact correct. There's nothing wrong with that in terms of where we left off. But our memory model actually gets changed with regards to this. It's not just an issue of something being statically allocated versus dynamically allocated. It's different than just when we do the allocation. They're actually allocated in different locations in memory as well. Think about that discussion we had about scope of our variables. All of those variables that are local to a function have that scope. They live there. They are valid for the life of that function as it's being called. So something declared in main will live for the life of your program, but otherwise your variable just lives as long as the function that it resides in. So static memory allocation is usually allocated only for the function in which it's declared, and then afterward it's gone, it's deallocated. Dynamic memory allocation is different, or memory that's dynamically allocated is different. It lasts until you explicitly deallocate it yourself as a programmer. Other programming languages have other ways of keeping track of dynamically allocated objects. You'll hear terms like reference counting and garbage collection, and C doesn't do any of that. You, as the programmer, need to be aware of it. From an implementation perspective, we already saw actually that as we call these functions, we have this data structure to store things called the stack. For statically allocated memory, the compiler makes use of the fact that functions will return in the order in which they're called. You'll have a stack frame for main, followed by a stack frame for foo, followed by a stack frame for bar. That's our first in, last out queue. That's our stack that we use for this purpose. So as we call main, main calls foo, foo calls bar, we can kind of stack things on top of each other as the functions are called, and then as the functions are returned, our memory gets returned back to us. The heap is different though, because not only is it not sort of automatically deallocated for you here, it can actually be allocated and then deallocated in any order. It's all sort of programmer determined memory allocation here. And that makes life a little bit trickier in terms of where we store things. Memory can get so-called fragmented, right? Where as variables of different sizes are allocated and then deallocated in different order and multiple times, keeping track of where things are becomes a little bit of a trickier problem. So for that reason, when we do dynamic memory allocation, it's actually not stored in that same stack data structure. It's stored on a different structure that is kept track of called referred to as the heap. If we go back to that 10.01 example where it was print pointer, you may have noticed that those statically allocated things were at really high addresses, whereas that malloc variable for C was at a much lower address. And go back and take a look at that if you don't remember. That's kind of an artifact of what we're talking about here. But there's a special data structure, and I think it's sufficient to know that it exists, and it's there to help manage where things are placed in memory. So in this example here, we perhaps have A, we allocate 10 integers, B, we allocate 20 floats, C, we allocate 10 more integers, and our heap layout will kind of grow as we do those allocations. Our function for deallocation is called free, and you pass it the pointer you want to deallocate. We want to put this hole or this fragment here where A and C are still live, they still exist, but we've gotten rid of B. The heap is going to take advantage of that available memory, and when it comes now time to allocate something else, although we can't guarantee for a certain malloc implementation it'll be in this exact location, but presumably, conceptually at least, D will then get put there on the heap. And then if there's room, E will go there next to it on the heap, because that's 5 doubles next. But maybe F now is 3 more integers, and actually if you do the math, we don't have enough bytes between E and C to store it there. In this case we do, but if it wouldn't, otherwise it would have to go where C is here. We should always be careful when working with our pointers to make sure that our pointers are never null before we use them. That's kind of a separate issue, but when you're getting a seg fault, that's a very common case where you're following or dereferencing a null pointer that corresponds to memory address location 0, and your user programs are not allowed to access that location in memory. So we have these stacks that we saw when printing them out grow from our high address is actually backwards. And our heap that actually, as we saw, grows from our low memory addresses forwards. Stack is growing and shrinking over time. Our heap is potentially growing and shrinking over time. How do we prevent them from running into each other? We actually don't. But in practice, because we start the stack at the top, start our heap at the bottom, we actually tend to be okay. And if we run out of memory, we run out of memory, and our programs aren't going to be able to proceed. So we saw that example, that idea of freeing memory. That is important. If we don't free our memory, when our program is done, our memory does get freed. So why worry about it, right? Let's just allocate all our stuff when we need to allocate it, and then at the end of our program, it all gets freed. Well, that can cause quite an issue. So if you look at this loop here, we're some while loop, it's some critical functionality, and somewhere inside that while loop, we're doing a malloc call with no freeze corresponding to it. So for this example, while it's a synthetic example, it could certainly correspond to some real code here. The memory keeps being allocated in a loop and is never freed until our application is actually done. That could be a minute, that could be hours, that could be days, that could be months away. That's what's referred to as a memory leak. And if you ever use Task Manager or Process Manager to look at your memory of your applications over time, even the world's very best experienced programmers have problems finding and fixing those. Even if your Google Chrome is sitting there and it's doing seemingly nothing, you may see the memory usage kind of tick up over time. Most of those are fixed now, but certainly all sorts of modern software still has issues with this problem. Conceptually, it should be easy to check. Hey, every time I allocate, let's make sure I eventually free. In practice, keeping track of that can be a pretty tricky thing here. So we have our malloc call, we have our free call, and then we also have two other dynamic memory functions we have to be aware of. There's calloc. It's like malloc, except it just initializes it all entirely to zeros. Then there's realloc, which we will be using more, which changes the size of some previously allocated region of memory. So we have a pointer corresponding to a dynamically allocated region of memory. We would then call realloc to either make it larger or make it smaller. And then we saw free here. Free is a previously allocated region of memory. So the functionality is actually quite similar to what we already saw with malloc here, but the syntax is, I would argue, is pretty annoying here in terms of the syntax here. Malloc, as we saw, just took a number of bytes as input. So you did, if I wanted to malloc 16 integers, I would do malloc 16 times size of int. For whatever reason, and I don't frankly know the reason, I'm sure there is a good reason, I just don't know it. Our calloc syntax, which does something very similar, it allocates 16 integers and just sets all the bytes to 0, passes it as two different parameters. 16 things I want to initialize, each of them are of size of int. Why isn't it 16 times size of int? I don't know. Likewise, realloc, well, it kind of makes some sense. We have to pass it the pointer, and then we pass it the number of bytes we're trying to write. I don't know what to say other than, you'll get some comfort, some experience in using these functions, and you always have the reference available when you need to look it up and remember what is the exact syntax of calloc versus realloc versus malloc versus free. It's really just those 4 functions in C, and you'll use them a lot in your programs, and you'll just get used to it. When you do it wrong, you'll get a compiler error, and you'll look back and think, oh yeah, that's right. Malloc has this syntax, but calloc does it differently for whatever reasons. So the first programming practice I want us to dive into is to try to build a more advanced data structure, because our use of pointers and dynamic memory allocation actually allows us to do more advanced things than what C arrays at least provide for you. So if you look at C++ and most other programming languages, there's a built-in dynamic type called a vector, which is like an array, except it's an array that can change in size over time, and it's also an array in which you can insert something at a particular location, and everything else kind of gets moved aside as we work on it. We can think of that array as being like a vector, as being like an array that just has dynamic memory allocation associated with it. So while most programming languages provide that facility for us, in C, we would have to write our own. So that's not the end of the world. I mean, we think about functions that we may want to write. It could be something that we want to do just once, and then hopefully never have to do again. So let's work on that again. So we can look at the documentation for that um, vector type here, although it's a little abstract as almost all C++ documentation tends to be. It's saying the dynamic allocation as part of its functionality, as well as here are the type of operators we may want to have to support, and there's quite a few. You can push things at the end, you can delete the last element, you can insert, you can erase, you can swap elements. It's a lot more flexible than an array, but there's no magic to it, right? It's the programming language itself providing this as a syntactical feature that you can just have as a data type, this vector type. But as an implementation perspective, just because it exists in the language, there's no magic to it there. It has to be implemented via some dynamic memory allocation, just like we are going to do ourselves. So let's give it a try. Conceptually, though, I want to make sure it's clear that when we think of an array, they're quite similar. Array is just going to be, let's see if I can draw this and have it work. Array is just going to be our statically or dynamically allocated region of memory corresponding to a variable type. And a vector is actually going to be quite similar. In terms of the location and storage in memory, it's going to look quite similar. They are just regions of memory where we're storing things. What is different when comparing the array type? Well, the array really has just one operator associated with it, right? Access an element inside that array. For a vector, you're going to have the ability to do things like insert an element here, or remove this element here, or dynamically append. That's just to say append an element here. But it's just a region of memory with functions associated with it. And when you think about other programming languages that have built-in vector type, that's ultimately what it is as well. It's a region of memory in which functions are defined for it to be able to do it. So I suggest as our implementation challenge here are a few different types of functions we may want to have. I don't say the exact syntax for them, but I think we can kind of figure it out, that there needs to be a function to create an int vector or a vector of integers of a certain type, to be able to resize it, and we're going to use that realloc for that purpose, to insert something in a location, to remove something in a location, and then just for practical purposes, we need to have a function to kind of debug, and so we're going to want to have like kind of a print function associated with here. That's what I meant when I say there's nothing new here, that it's just a dynamically managed array. So but in theory, and what would be nice about it is if we wanted to do this in our C programs, we could create this library, these functions once, put them in a library, and then never really have to think about them again. Let's give it a try. This is not the entirety of what would be a C++ vector type that we'd be creating, but it gets us kind of started here. Again, the actual reference only helps us so much. I think what's probably more helpful is just looking at those functions. What are the functions that we need to create for this? And I kind of just list them here in this example that you can find on Replit, which is create, resize, insert, remove, and print. It's not really clear what order we want to start with these, but let's just kind of dive into this. So I call this int vector fun as an example. Well, fun is relative. I'm going to have fun at least, and following along, hopefully you'll have some fun as well. We need to actually have the data corresponding to that vector. So in this case, it's an int vector. The C++ version is much more dynamically templated, but an integer type is fine for us. We need to have associated with the vector, at the very least, some variable that's storing the pointer, as well as some other variable to store the length of that current vector. So I'm going to make these global variables. They don't need to be, but it makes our life a little bit easier in terms of implementing our functions. So normally, though, we would put these into a struct, but in this class, the way I've structured it, we haven't covered that yet. So we have two global variables representing what our vector is going to be And then let's start with our main. So we have our main. And we're going to have these functions then corresponding to these vectors. So, we have the 5 functions here. Which ones do we really want to start with? It doesn't really matter. I guess you can't really do anything if you haven't created a vector yet. So we'll start with that first function prototype and implement that one. We talked about how it's useful to have your function prototype first. We got to declare that in this case, it'd just be a void because we're updating a global variable. And the nice thing about having your prototype first is then when it comes time to actually implement the function, you kind of just copy paste that, right? And then you at least have a function that does something. So then we can have inside our main function as we get started here, let's call int vector create, and let's create our vector of size, I don't know. And then we are going to have to print it. So let's create that one next. Int vector print, since it's that global variable, we really don't need to have any input to it. Again, we could have passed that pointer and it would have been fine, but we actually don't need to. Okay. So, okay, we have some structure here. We can call create, we can call print. Always a good sanity check. This code doesn't do anything. It shouldn't complain, shouldn't crash on us at least. Okay, our code doesn't do anything yet, but it's there for us. So int vector create creates an array of length. So this one's maybe even a little bit easier than some of the others that we're going to create because we have these functions for memory allocation. We have our pointer that we're going to want to update. So we're going to want to allocate a vector of length, and it's just doing memory allocation. We have that function call. It's malloc, right? Malloc takes as input the number of bytes we want to allocate. And I know I'm working kind of from right to left here, but it'll be okay. We know its length, that's the input. LEN length is the input. And each of them, because it's an int vector, is of size of int. We then want to assign that output, because it returns an address, to a pointer. And to make our compiler happy, we want to cast that output so that it knows it's the right size pointer here. We also have this kind of global variable keeping track of what the current length of the vector is, and that's just a simple assignment then. Then we provided this, it's of length. We just want to make sure we've updated that global kind of storage of how long our vector is currently with that variable length here. That's correct. We have these other functions, right, of doing dynamic memory allocation in which we initialize the memory to all zeros. I would argue that's probably the right one to use for this case. I think it's fine with this. I would just say there's a valid debate that I'll say here. Malloc is fine, but should use calloc probably. And what would that look like then? It'd be very similar. And except now the syntax, for whatever reason, as I mentioned, just passes the length separately. Okay. And then we have our function print, which we know is part of that is going to be a for loop. We want to just print our values here. So this is something we've done a lot of times. If we want it to print nicely, let's do the last element separately. Right, we have that global variable. It can access that global variable vector, print out each value. Let's print off the actual length. So let's make it look like, hey, a vector of this size is this. So we go through we print a little header. We go through the array. We print each value with a space at the end. And then, as our special case, let's print that last value. I know it's annoying, but we've done it this way all semester. And once we've written this function once, we never have to worry about it again, right? So int vector print prints out the length information, makes it look like a nice little array syntax there. Goes through the currently stored length of the array, prints the value with a space, and then finally prints that last value and does a little new line at the end. So it looks a little bit nicer. Create a vector size 5, hit print, should print out vector 5 is 5 zeros. Well, we're 2/5 of the way done already, right? Let's take a moment and just review what we've done here, right? Int vector create is doing our dynamic memory allocation. This code would not work correctly if we called int vector create multiple times, that we're using that same array, global array variable. We would have a memory leak if we did that. But for our purposes, if we just know we're creating a single int vector here, and we're going to create, you call the create function exactly once with it, I think it's okay from that perspective. And then, we've done the dynamic memory allocation, at least for purposes of printing. That int vector print doesn't really look any different than any array print we've already been doing back when we've started with arrays. So far, dynamic memory allocation is new. The rest of that's pretty conventional here. Um, at that point, then there's really, nothing that interesting happening. We have to do something. We have to actually set the values in the vector. Right? We want to have non-zero values here. So any kind of for loop will work. I mean, and it doesn't really matter. What do we want? Vector of I don't know, I squared plus 2 or something like that. And just to confirm that that works, let's just print it again. So, and again, this is just arbitrary. What do you want to say? Like arbitrary init. We could have done rand and things like that. In this case, a simple for loop that initializes it. We get our values. I squared plus 2. That's 2, 3. That looks correct to me. Now, we're just kind of writing code that tests out our function here. Resize to length 7. That's something that an array by itself we can't do, but with our dynamic memory allocation now, we can say, hey, take that array that was a vector that was of size 5, and that was our resize function, and now let's make it of size 7. Resizes array to length. Got our prototype. It doesn't really matter where we put it then. Let's put it somewhere. Let's put our print at the end because we're not going to have to change that at all. Here's our resize function. And the nice thing then, I guess, about this resize function is it involves, dynamic memory reallocation here. And we have the function that does exactly that. Pass in the pointer, pass in how big you want it to be now, and we have that function. So this is really just a kind of a thin wrapper around our existing realloc function that we have here. So we do have to call realloc. Put a little note here. Call realloc to resize. And our syntax looks kind of similar to our malloc, except that we have to pass now the original pointer. And you don't have to set the result as the same pointer, but it makes sense for our purposes that we are. And the new number of bytes. Now, and then we do know that at the very end, we have to set the updated length to that new length from 5 to 7. We should probably initialize any new memory to 0, because realloc will not do that for us, and we took the trouble of allocating things to 0 in the first place. With our REPL environment, we maybe wouldn't really notice if that was the case. So if we've allocated more, if we've grown the vector or extended the vector, if our vector is now larger, if our length we've passed to this function is greater than the length that it originally or previously was, we want to go through and make sure that those values, and only those new ones, is equal to 0. So we have a vector of length 5. We initialized it to those values that we have printed out there on the right. We're now resizing it to length 7, and for array element 5 and 6, or the 6th and 7th element in those arrays, we'd want to make sure that that value itself gets initialized to 0. It probably would be 0 anyway in this environment, but we're fine if we do that. We should now have 2, 3, 6, 11, 18, 0, and 0. We have a pretty cool data structure so far that you can set as a user of this functions you've written. You don't have to worry about dynamic memory allocation yourself. You just call resize. You get your vector of different lengths as you go. We then also have like that insert functionality. Insert, does it even say exactly where it should be? Yeah, insert a value at location 2. So int vector insert, I mean, do we care what the value is? I don't know. The value of 9 at location 2. The problem with our syntax here is we'll get it confused about which one is which, but as long as we have a clear function prototype, we won't get it backwards ever. There's our insert. Takes a value to insert and a location in the vector to insert. So going back to our whiteboard here, I didn't draw it all that well, but the idea is that after you've done this insert, so if we have this and then we call insert 3, the end result, and I guess it would be insert at location 3, insert a val at location 3. The end result would be an array that's one length larger. The previous elements would be fine. Then there would be that val now at location 3, and the end result would be an array that's of one length longer because we've inserted something. So this is both like a dynamic memory allocation as well as an updating of our array. We have to actually do both for this here. Now, the nice thing about our insert function is as I said, we have to do a resizing of it. But we have a function already to resize it, right? We could rewrite it here and do realloc and all that inside this function. But we already have that nice int vector resize, and our length has to go up by 1. So another comment here would be resize the vector by 1 or something, right? Increase length by 1. That's me being clever. I could do length plus plus and then resize length, but that works pretty well for us. So we have whatever the current length is. We want to increment it by 1. That's going to be our new length here, and so that does work for our purposes. Then we have to actually go through at that location. We have to kind of copy things over. So what would the comment be? At the what would be the right way to phrase that? Copy things over starting at location low. So we have to explicitly do that. I don't really, again, I didn't show it all that well in the dry erase board version here, but if there was some values x, y, z, they still need to be there in the array. W, x, y, z here. We have this val here. We still need w, x, y, z. Everything is just going to be kind of moving its way along. So, and while we've reallocated the array is of length 1 more. So that previous function call does work as intended. Things don't magically just get kind of moved over. We have an array. It would be of length 1 more. That final new element of length 8 here, I guess here at index 7 would be a 0. So we do need to make sure we're kind of manually then shifting things over. There's a memcopy call that would probably do this for us really well. I think a for loop would just work pretty easily for us. We probably, I haven't thought about this. We probably have to start at the end and make our way to that value that we've just inserted. We could do it either way. You just got to make sure we're not overriding things. So our vector of I plus 1, so that'll be the last element we start with. Is going to be set to be that vector of I. So length minus 1, vector of I plus 1. So I think it should be length minus 2. So vector of I plus 1, that's the last element, is what the one next to it would be. No, I see how we have it here. So length minus 1. It's got to be that. Length minus 2. So we have our last element that's now at length minus 1. That's the one we have to update it. That's got to be set to length minus 2. So we take our z, move our z over. Then we take our y, move our y over, etc. Take all of those over. We do need to finally update it, including the value that was currently at location. And then we actually have to update. That's the final part there, Update location with the input value. insert a value of 9 at location 2. Let's make it 99 or something like that so we can see it more clearly here. Value at location 2, let's print it again. 0, 1, 2. Fingers crossed on this one, folks. 0, 1, 2. That does actually work. Okay. We resized it. That's why there's still 2 zeros at the end. But 0, 1, we've inserted at location 2. I guess we have to be clear that we're starting with 0. So location 0 would insert it at the very beginning. This one's inserting it at location 2. Our insert function appears to be working well enough here. And then finally, we have that remove function. Let's remove the value at location, doesn't really matter, location 4. And this will be the last thing that we would have to implement here. So we have int vector remove, removes value at location. Location. That's our prototype, as well as can help with our implementation. This should look kind of similar to our insert function. So let's, just for kind of copy paste purposes here, it should look very similar to what we're doing here. Thinking about this a bit, right? We have to remove the value. So there's this kind of like copying operation that happens first. Because here we're making it one size smaller. We have remove. So after calling remove of this x, we wind up with an array that is now back to what it was before, but as it turns out, one length smaller. And we still have those things in there. But now there's no x, because that was what was at that location. So we have to be a little careful, right? If we did resize first, that would be wrong. We would lose whatever's at the end of that array. We have to copy things and kind of overwrite that location of x, move everything back down one, and then we can do the resize. I don't expect you to know this from base principles. This is just something that, as you draw it out, you kind of think about what operations are required here. This is not something you have to do for your programming practice, but it's just an example of working with our pointers here. So we do have to copy things over. So starting at loc, it's kind of the same exact opposite of what we had here, right? Before it was vector vi plus 1 equals vector vi. Here we can do it as vector vi equals vector vi plus 1. There's more than one way to do it, but that would do it, right? Starting at location, overwrite that location with whatever is next. Then the next one, continue, continue, continue. You then would technically have a duplicate copy of whatever the last element is, but then who cares in some sense, because now we can just call our int vector resize. We did plus plus length, now we do minus minus length by -1. We copied things over. We technically had a duplicate entry at the end, but now we've reallocated the memory. It's not part of the array anymore. Would not be the first time I created a terrible compiler error. Int vector remove. Removes value. Cannot find int vector remove. Here's int vector remove. Int vector. It's good to see me get an error, right? Not infallible. Cannot find. So when you see an error like this, I've written a function. I think the function's there, but when it says undefined reference to int vector remove, it's not even. It is going to tell me it's on line 110, but that's not a surprise. That's where I wrote it. What did I do? Int vector remove. In vector. I guess it's a typo. Hey, won't be the first time, won't be the last time, and it cost us some time there. Element 11 got removed. So it actually did work. It's kind of a dynamic resizing where we remove one element here. That example, and it's there, and you can take a look at it on REPL and kind of explore how we did that. That's just an example of just using those dynamic memory allocation functions and playing around with the different things you can do with it. I want to go through one more example. So pointers are hard. We're going to do a third video for pointers where we're going to look at a little bit more dynamic memory allocation, and using pointers to allow us to do things that otherwise would have been a little tricky with just our static memory. So stay tuned for an unprecedented part 3 video for this learning module.